try to review atoms in electromagnetic fields, and then look up the semiconductor devices. Let's see how we'll be able to get going. So in our last class, we made mention that when atoms are exposed to some external field, say electric field or magnetic field, we experience some kind of effect. And when we consider the interaction of atoms in electric field, we say, well, we experience what we call the stack effect. And if it's exposed to the magnetic field, we experience what we call the Zeeman effect. And the bottom line is, in our study, we want to figure out the motion of this particle in that space. And as such, we'll have to designate the Hamiltonian, because with the Hamiltonian, we are able to tell the energy. And with that, we are able to also specify some other interesting parameters, including the momentum and every other thing we could tell, or we may be interested in telling about that particle. Okay. So let's jump into this. Okay. So let's say a quick review of atoms in electromagnetic field. Okay. So we made mention of the stack effect and the Zeeman effect. So here, we say that the stack effect is the splitting of the atomic spectrum due to electric field. Okay, why the Zeeman effect is the splitting of the atomic spectrum due to magnetic field. So when we talk about the splitting of the spectrum in this case has to do with the energy levels, okay? So we want to, what we actually mean here is the splitting of the energy levels due to some background field, be it electric or the magnetic field. And if we should consider the stack effect, when electrons are exposed to some electric field, for instance, then we know that in this case, the electron we have to interact based on the field effect. And if we assume that the field, say E, the electric field, is in the direction, say Z direction, then the potential energy in that direction, V of Z, will be the same as the charge, say E times the field minus the Coulomb relation, which is E squared pi epsilon naught R. Okay? Now, if that's that, then the Hamiltonian will be the kinetic energy plus this relationship. So that's going to give us h cross squared over 2m Nambla squared minus E squared over 4 pi epsilon naught R plus E EZ, where E is the electronic charge. Okay? And we also know that the strength of a typical field is about say, approximately 10 electron volts per centimeter, okay? And the ground state, which you already know, going by the Bohr's ideology, is about negative 13.6 electron volts, which you could derive. And then with all of those, we should be able to estimate some other parameters, okay? And with this, we should be able to tell what actually goes on, okay, when the electron, when we now have to analyze the effect, or better still, tell the information about the particle within the electric field. And this becomes the Hamiltonian, okay? So if we should consider a linear stack effect, for instance, I'm just trying to run through, more like, then we know that the uncertainty in the energy is given as the bra of the wave function, then E dot x in the x direction, for instance, then the ket of the wave function, which is the same as negative P dot E, okay? Where P in this case gives us the electric dipole, okay? So now that we have introduced the electric dipole, it means that P is the same as the negative E bra of psi x, then ket of psi, which is the same as the negative of the electronic charge, because this time integral, we're looking at this in the three-dimensional space, then x, then that's the cube x, then x mod psi of x squared. Okay, but the bottom line is, here we are talking about the electric dipole. So the bottom line is, what is a dipole? Now, in our previous note, which you already have, we made mention that the dipole, let's just put that down, that the dipole is the separation of charges within a molecule, okay? Usually between two covalently bonded atoms, covalently bonded atoms, or atoms that share an ionic bond, okay? Now, we already know what a covalent bond is. When we have two atoms sharing electrons, then we form a covalent bond. But should we have an atom donating electrons, then we have ionic bond, right? So we know the covalent bond has to do with sharing of electrons, right? Electrons between two atoms, while the ionic bond is formed when we have to donate, okay? Donation of electrons, okay? By one atom to another. So if this is a dipole, which has to do with the separation of charges within the molecule, okay? Then how about induced dipole, okay? Because we're going to be playing with these parameters. Induced dipole. So when we say induced, what we are trying to say is that something causes this, okay? So an induced dipole would be one caused by an external field, okay? So this now is one caused by an external field. So that is why it is induced, okay? So it could be, this field could either be an electric field or a magnetic field, okay? So what about if we have to relate with that of electric field? So let us see electric dipole. for instance. So it means that the potential energy in the electric field is given as V being the same as negative P dot E. Okay? Where P in this case is the dipole moment, and E in this case is the electric field. And you'll observe that the electric field goes from negative to positive. Okay? And that's the electric dipole, right? This electric dipole, we are moving from negative to positive, which is contrary to the direction of the electric field itself, okay? Because the electric field itself moves from positive to negative. So it means that at some point, this electric dipole will result in a reduction, okay? And if we should consider the magnetic dipole, for instance, the magnetic dipole, now the potential energy here will be given as V being the same as negative mB, where m in this case is the magnetic moment and B is the applied magnetic field, right? Same with what we have for the electric field, but there's a difference here, okay? Recall that the E field moves from positive to negative, while the electric dipole moves from negative to positive, right? But for the magnetic field, you will recall that it goes from north to south, okay? That's the external field, okay? Outside, you know, the magnetic field. So if we talk about outside the magnet, for instance, so outside, so we have outside the magnet, and we have inside the magnet. We're just trying to review your basic physics here. So here it moves from north to south pole, and inside it moves from south pole to north pole, okay? And this is the same direction with the magnetic dipole. So such that magnetic materials made out of magnetic dipole causes the magnetic field that turns the dipole to increase because they're in the same direction, both external and internal, okay? And for the electric field, because of the difference in the direction, it causes a reduction. So when we talk about the materials made out of electric dipoles, you know, they cause the electric field that turns the dipole to be reduced, okay? And now with this, I will just quickly mention one other important thing, which is your induced electric field. So for an atom, let's say we have an atom in which the center of the negative cloud of electrons has been shifted away from the nucleus by an external field, just like, say, electric field this time. Constitutes what we call an induced electric dipole. So basically, you should be able to tell what the dipole is, what the induced electric dipole is. Then you should be able to tell what the electric dipole is. And you should be able to tell what the magnetic dipole is, okay? We just mentioned these four parameters, okay? And then with this, we already established some basic information about the Hamiltonian when we have to relate with the electric field. But how about for the magnetic field, the Zeeman effect? Okay. Now, when we talk about the Zeeman effect, the addition of a magnetic field in this case results in an extra term in the Hamiltonian, the same way we resolved that in the electric field, the stack effect. And this arises because the electrons are charged, and as such, the kinetic term in the Hamiltonian will now become, say, H being the same as 1 over 2m P plus EA squared minus 1 over 4 pi epsilon naught Z squared over R. And we know A is a vector potential from our electromagnetic field, okay? Potential. And then the magnetic field is given as the cross of A. So if we take the magnetic field in the Z direction, for instance, the way we also observed or viewed the electric field, so it means that B is the same as B in the Z direction. And let's say through the symmetric gauge, then we have that A will be the same as the magnetic field over 2, then considering X, Y. Now we have 0 in this case because the field is in the Z direction. And then the cross terms here, P dot A will be the same as A dot P, be the same as B into bracket XP sub Y minus YP sub X divided by 2. Okay. Now, if we recognize the combination in bracket here as the component of the angular momentum in the Z direction, then we can tell that the angular momentum Z, L in the Z direction will be the same as XPY minus YPX, right? And if we have this, then we can now rewrite the Hamiltonian to be the same as H being the same as 1 over 2m P squared plus EB dot L plus E squared B squared into bracket X squared plus Y squared minus 1 over 4 pi epsilon naught ZE squared over R. Okay. And you'll observe that B dot L assumes the characteristic form of the energy of the magnetic dipole moment, mu, okay, in a magnetic field, okay? And then we already mentioned the magnetic dipole, okay, the potential, which is the same as VB, the same as negative MB, okay? So, so with this, we could run some further analysis such that mu L, we can show that mu L is the same as negative E over 2m L, okay, the angular momentum, okay? And then on and on. So here you observe that this is the dipole moment that arises from the orbital angular moment of the electron, because we have to consider L, okay? And by way of extension, we now have this to be the same as 2m over 2m where this is the G factor, which is usually very close to 2, okay? And with this, we are able to define the Zeeman Hamiltonian, okay? So here at this point, I'm actually ignoring all the necessary derivations. So the Zeeman Hamiltonian will now become E over 2m, E over 2m, B, L plus 2s, okay? And we know that the total angular momentum, J, is the same as L plus S, okay? That couples the magnetic field, okay? And also, the dipole moment, mu total, will be the same as negative E over 2m, L plus 2s, okay? So this we could show. And when we talk about the strong Hamiltonian field, then we now have to resolve H being the same as H naught plus the Zeeman Hamiltonian, okay? And this is going to give us 1 over 2m Nambla squared minus 1 over 4 pi epsilon naught ZE squared over R as defined earlier plus E over 2m B dot L plus 2s. Okay, so semiconductor devices. Okay, so why do I want to talk about devices? No, I don't want to talk about devices. So I want to talk about semiconductors. Okay, the physics of it. Okay. Okay. So, well, if we have some time, we'll go into talking about the carrier transport and all of that. But our major focus here is that we have some materials, okay? Some elements in the periodic table that pose some interesting properties or characteristics, okay? And now we want to see how these parameters or elements interact. Should we bring them together, or should they, say, act alone? Okay, so what's going to happen? And in their purest state of form, what do we expect to observe? And should we add some impurity atoms to them? So what is also going to happen? So those are the things we actually want to consider in this case. And if we should experience some level of deformity in the material medium, for instance, so what is going to happen? So that brings us back to the quantum well ideology. Okay, so that's about what we are going to be interacting with from time to time in the study. We have a quantum well. Let's see if we'll be able to describe the Bloch theorem, okay? So here we have atoms spaced in this manner. So in this manner. So this is V of X. So we'll have that this comes all the way, and this comes all. So there. So between this and say this, we have our distance L, for instance. So here we have 0. So this is negative d over 2. This is positive d over 2. Okay, so this actually shows a linear array of ion cores, which are the solid dots, okay? And then it also shows the periodic crystal potential, which are these solid cores, okay? So these cores are the crystal potential, while these dots are the ion cores, okay? So we have this distribution, okay? So if we should consider the nearly free electron model of solids, for instance, then we should be able to define the Bloch theorem. That's Bloch theorem. Okay. And then specify some other interesting parameters. But let me start with this. Now, the Bloch theorem actually tells us that the Schrödinger equation in a periodic potential takes the form of a plane wave, okay? Modulated by a periodic function. And if we should evoke the, what's it called now? De Broglie wave equation, we have that the wave number is the same as the difference, or better still, the ratio of the momentum and the reduced Planck constant, which is the same as square root of 2m over E over H cross, for which we can estimate the wavelength, right? And we know that the crystal momentum is the same as H cross K, okay? So from Bloch theorem, in relating with the Bloch theorem and the de Broglie wave, we now see that the de Broglie wave of an electron in a periodic potential wave region is a partially amplitude modulated wave, okay? And this has a periodicity equal to the lattice spacing, this spacing here, of the periodic structure, okay? And with this, we can now say that this is what you already know from the Schrödinger equation, that H cross squared over 2m, the x squared, plus v CR of x, psi of E of k of x is the same as E of k, psi E of k of x. Okay. And then we can evoke the Born and the von Karman's theorems, okay, or boundary conditions to resolve this. Well, we don't want to go into all of those solutions right now. You already have them in the notes, so we'll just try to move on, okay? So I also don't want to go into the density of states and the Fermi-Dirac distribution function, which has been covered. So I think now I will just make mention of a few tips. Okay. So now I know also in one of the classes, I made mention of the elements, okay? So here we have boron, aluminum, gallium all the way, okay? Then here we have carbon, we have silicon, we also have germanium all the way. Then we have nitrogen, phosphorus, then we have arsenic, we also have antimony, bismuth, and all of that all the way, okay? So the idea is, well, we also mentioned earlier that silicon is more temperature sensitive, stable rather, than germanium, okay? And looking up this periodic table, group 3 elements have 3 valence electrons. Group 4 elements have 4 valence electrons. And group 5 elements have 5 valence electrons, okay? So we could combine group 3, group 4 elements to form some kind of interesting semiconductor devices. Also, group 4 and group 5. We could also combine group 3 and group 5 elements, the likes of gallium arsenide, okay? So here we also have the indium, right? So we could also include indium, gallium, arsenide, okay, when we talk about the quantum wells, okay? So we could form some other compound semiconductor devices, depending on what we want to achieve, okay? But the bottom line here is that we want to deal with 2 major types of materials in this case, okay? Now, coming from the intrinsic perspective, where they exist in their pure form, okay? And once we have some of these atoms, they form some kind of crystal. So let's assume I take a silicon, for instance, which has 4 valence electrons. So for the silicon, we're going to have something like this. We have 1, 2, 3, 4 in the outermost shell. So this can also bond with another silicon atom, where we have 1 here. So that forms a complete bond. So let's say we have another one here, another silicon here. This forms complete bond. So recall it's also 1, 2, 3, 4. Here 1, 2, 3, 4. So we can have another silicon atom here. So this forms a complete bond. So we have 1, 2, 3, 4 here. This is also silicon. Then we can also have another silicon atom here. So this is 1, 2, 3, 4. So this forms a complete bond. Okay. Yeah. So with this, we actually form a crystalline solid, okay, which is completely filled. And here we are able to say devise some intrinsic materials. But what happens if, for instance, I introduce an impurity atom here? So where we are supposed to have a silicon, let's assume we have, let's say gallium, or one of the group 3 elements, okay? So it means that we'll have 3 valence electrons here, and then here we'll be having 1 hole. What if we introduce a group 5 element? So we are going to have an additional electron, okay? So whether we have an additional electron or a hole, this is going to lead to net movement of either holes or electrons. So that effect will result in what we call the extrinsic material, okay? Now, which the Bloch theorem tries to resolve and all of that, you know? So I'm just trying to jump the gun at the moment and then come up to this part, okay? So If we now consider such a material, okay, where we now have to deal with introducing some impurity atoms, and then we already know that if we should bring in a group 5 element here, we are going to have an additional electron here, which is a negative charge, okay? So it means that at room temperature, this will be mobile, okay? And once it is mobile, it's going to lead to a net electronic charge movement in this device, okay? And then automatically, this device now acts more like a donor because it has an electron it could give off, okay? And then we say that is an N-type material. So if, for instance, it is a hole, okay? So we do not have the electron here. So and now this silicon is no more a silicon. So this is now a hole, right? Not an electron. So let's assume we have one of the group 3 elements here. So it means that this hole will result in a net movement of holes. So it means it can actually accept an electron, okay? So it becomes an acceptor, a p-type, okay, material. So if that is what we have, then it means that if, for instance, we now try to design, or better say device, a system where we have the p-type material and the n-type material, okay, mesh together, for which we can say this is a junction. We say we have a PN junction device. So I think this is of interest today. I just want to talk about the PN junction devices, okay? And then see what we could, work around in this case. Then if we have some more time, then we'll try to derive a few things, but just want to do some talking today. Okay. So if we talk about the PN junction, for instance.
Few guys in the picture. See, but
Okay. So we see that for a PN junction device, we can refer to the PN junction as a metallurgical and an electrical junction between P and N-type materials. Okay? So when the materials are of the same type, we say the junction is a homojunction. And when the materials are of different type, we refer the junction to be a heterojunction. Okay? So the idea now is we have this is a PN junction here. Don't want to take that off. So this is the p-type, and then this is the n-type. Okay. Now, we experience an effect here. Okay. For the p-type, we see some negative charges here. For the n-type, we're going to explain this shortly. Okay. Okay. So here we have majority carriers and the minority carriers. Okay. Now, for the p-type material, what we have here are holes, right? So the majority carriers are holes, but it does not mean that we do not have some electrons. So because the holes are more than the electrons, we say that the minority carriers in the p-type material are the electrons, while the majority carriers are the holes. Now for the n-type material, we have electrons all over this place, which forms the basis for the majority carriers. And then the minority carriers becomes the holes. Okay. So what I want you to look up here is that the majority carriers diffuse. Okay. So the majority carriers diffuse. That is, holes we move from the p side to the n side, while electrons will move from the n side to the p side. Okay. So it means that electrons will move in this direction, while holes will move in this direction. Okay. So that will give us a net diffusion current. Okay. And we now realize that as electrons move from the n-type material, or the diffuse from the n-type material to the p-type material, they leave a positively charged ion. Okay. So the next point I want you to take note of here is that bare ionized dopants are exposed on either side of the junction. Okay. So positively charged donors on the n side and negatively charged ions or acceptors on the p side. So as the holes diffuse from the p side to the n side, it leaves a negatively charged ion, you know, at the junction. And then this results in what we call the depletion region. Okay. So the dopant ions are therefore combined in the region of reduced carrier concentration. Okay. And the region, we'll call it the depletion region. This becomes a depletion region. Okay. Okay. And something I wanted to take note of at this point is that the process of diffusion will continue until the depletion region expands to a certain width. Okay, such that the electric field in that depletion region is large enough, or now becomes large enough to repel the diffusing carriers. Okay, so this depletion region will continue to expand till a state where you say, well, the diffusion current, J diffusion, is now equal to the drift current. Okay, and there we say that we have established the equilibrium state, okay, or situation. Okay, and then this brings us to the analysis, because once again we are going to recall the Schrodinger equation, okay? Because we are now talking about a net electric field, okay? Because this depletion region here have a positive charge and a negative charge, and this will result in an electric field in this region, okay? So one thing you should know is that the driving force for the carrier motion is what we refer to as the potential, or the electrochemical potential difference, okay? And this exists between the two semiconductor materials, the p-type and the n-type. And then we could derive some mathematical deductions. So what happens in this instance, okay, when they are separate, we've not combined them. We have the p-type material, we have the n-type material. So let us look at that quickly. And then when we combine them, what also happens? So for the p-type, okay, this is what we have. Okay, let's split the board. We have the p-type material here. We have the n-type material here. And here we have the p-type and the n-type material here, okay? So for the p-type material, we know that here we have holes, right? We have holes as the majority carrier. For the n-type material, we have electrons as the majority carrier. So if we should put up the band diagram, so we know at this point we have the conduction band, and then we have the valence band. So the Fermi level will just be above the valence band. Let's move this. That's the FP, right? For the p-type material. And also for the n-type material, we have the conduction band. And then we have the valence band. And then we know that the Fermi level for the n-type material will just be below the conduction band. So here we have E, F, N. Okay. And now we will have to define the work function. Okay. So let's assume here is some distance. So let's use another color. Let's change the color. So let's say this is, let me change that. Let's say this is some distance, x in space, okay? So this just gives us an idea about vacuum, right? That's some distance in space, okay? So now we can describe the distance between this to this, and then we can also describe the distance between the Fermi level and this. Then we can also describe the distance between the valence and the conduction band, okay, for both materials, okay? For both materials, we can describe that. Then we can also, so let's assume we extend this line all the way. So let's assume we extend this line all the way. We extend this line all the way, okay? So then we can also tell the distance between this to this. Then we can equally tell the distance between the Fermi level and this point, and the Fermi level at this point. We can also tell this distance. Then we can also tell this distance. Now, all we just want is the work function, okay? Now, if we say this is Qx, then this distance, which spans the Fermi level and this position, is the work function, which is Q phi of P for the P material, okay? And the same distance relative to vacuum and the Fermi level for the N-type material is the work function, which is Q phi of N, okay? So this is also Qx, okay? Now, this is the energy band gap, which is the space between the spacing between the conduction and the valence band, okay? So this is say Eg and is the same as this Eg, okay? And now this distance, therefore, will be the difference between the two work functions, okay? This work function minus this work function will give us this distance, okay? So that this will be Q phi of P minus Q phi of N. And this will give us the same as the difference between the energy band gaps, Fn minus okay. Now, this is what happens before we form a PN junction, okay? These materials are separate, okay? And you should know that in this case, that the Qx is the electron affinity, okay? Electron affinity. So we can measure this in electron volts, okay? And we know that EFP is the Fermi level for the p-type material. You can also call it the electrochemical potential of the p-type material, while EFN is the Fermi level for the n-type material. Okay, or better still, the electrochemical potential of the n-type material. Okay. So we already know that Q of phi P and Q of phi N is the work function, okay, of the two materials. Okay, just more like say your state function or whatsoever. Okay. Okay. Now, what happens when we bring these two materials together? Now, at equilibrium, okay? So if we now have to form this at equilibrium, so it means that the energy levels for the Fermi levels for the p-type material and the n-type material will be equivalent. They will be equal at equilibrium, okay? And then it means that at equilibrium, let's put it that way, EFN is the same as EFP is equal to the Fermi level, okay? So when we do this, so it means that this particular line and this particular line will have to be equal. So it means that the p-type band here, band diagram, will have to move upward or relative to the n-type, or better still, the n-type band diagram will have to come down. So it means that we have this, for instance. This is EC, EF, P, EV. And should this come down, that is EFN. So it means that the conduction band also comes down so that this can be equal, right? The way we have this, so we have EC here. So it means that the valence band also will come down, EV. So that is why the band diagram is usually something like this. Okay, so this is what you see in most of your documents. Where this distance here, let's change the color once again. Where this distance here is the band gap. Okay, so this is the band gap. This is the band gap. Okay, and then we can also tell the depletion region this will be the depletion region, which is equivalent to this region. So going by this, the depletion region therefore has a net charge, okay? Recall here we have the majority carriers to be holes. So once the holes diffuse into the n-type material, they leave a negative ion, while here we have electrons as the majority carrier. So once they diffuse into the p-type material, they leave a positive ion, right? Okay. So it means that in the depletion region, we have a net charge, okay? And as such, the bands now have a curvature following the Gauss law, okay? So this curvature here follows what we refer to as the Gauss law, such that the E, the X, if we say here, if for instance, we say this is negative SP and this is positive XN, then is the same as rho over epsilon. Okay, so E is the electric field here. Or better still, in terms of the potential, the squared V over the X squared is the same as negative rho over epsilon. Okay, and then this is about the same as saying the squared is C the x squared is the same as rho over epsilon. Okay? So the net charge is equivalent to the curvature of this band. Okay? This curvature is equivalent to the net charge. Okay, so you want to take note of that. Okay? And then we can now describe, having the schematic, then we can therefore discuss here the charge profile, the electric field, and the band diagram. And we know that for the intrinsic material, the energy band gap is somewhere in the middle, right? That's E intrinsic. Okay, so all of these, what we just described here is that the material has been doped, right? But if it's intrinsic, then the energy band gap is not tilted in this manner such that it is just above the valence band for the p-type material or just below the conduction band for the n-type material, somewhere in the middle. And then we are going to have something like this. Okay, for the intrinsic material. So E intrinsic. Okay. Okay. Now, from the Fermi-Dirac statistics, I'll just quote a few things and then move on so that we've derived so much already. So I don't think I want to go on deriving at this point. Okay. So if we now have to talk about the built-in voltage, okay, for instance, we want to estimate that. We already made mention of the work function, right? Yeah, we made mention of the work function here. This is the work function, right? So we already know that this difference is the same as V times the charge, which is the built-in potential, okay? The barrier potential. So once we pull that up, then we should be able to provide some derivations, okay? So let us so since Q VBI is the same as the work function P, Q, the work function N. Okay, so the built-in potential here is the internal potential energy required to cancel out the diffusive flow of carriers, which we already mentioned. Okay, so and as such, we're able to have that depletion region. Okay, so it's more like it creates a balance. Okay, we are able to have this depletion region for the P and N-type material. Okay, so the barrier potential is what we're trying to figure out this time. And once we have this, we already know that the energy, IP minus the intrinsic, is the same as Q VBI. Okay. And once we run through the manipulation, so I'll just say P naught will be the same as Ni epsilon E sub I minus the thermal energy. Okay. And for the N naught, we have Ni epsilon E sub I minus the Fermi level divided by KT. Okay. And once we plug in all the necessary parameters, because this is the same as the concentration. So once we plug in all of those parameters, and we know that the work function, for instance, let's, okay, Q VBI will therefore be the same as KT, the natural logarithm, NA. Now, if that gives us the built-in potential, then we should be able to work out some other parameters and then check out what happens in the forward bias and in the reverse bias condition. So once we forward bias this device, for instance, so it means that this is the p-type, so we are going to apply the positive potential, and then here we're going to apply the negative potential. So this is forward bias. So it means this is going to repel all the negative, and so then the depletion region will reduce for net flow. And if it is reverse biased, for instance, then it is reverse bias. So this negative, this is positive. So it's going to, attract all of these, the positive charge, the negative charge, then this becomes larger. So the depletion region will act more like a resistor, a large resistor. Okay. So there won't be net flow of current. Okay. And then recall for this, so in this case, it becomes way larger, right? But this becomes narrower, okay, for both the reverse and positive bias, okay, forward bias, okay? And then there's something else I want you to take note of in this case. Okay. 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 Perfect. Now, if we have established that the built-in potential in this case is given in terms of this relationship, then how do we estimate the depletion region? It's that width, okay? So how do we estimate that width? Say this width, W, okay? So also by deduction, we see that this is the same as the square root of 2 epsilon over Q equals on B over NA and B VBI. Okay? Such that if we now consider this in equilibrium, then we now have this, which is the same as 2 epsilon Q 1 over NA plus 1 over NB VBI. So I want you to take note of this expression.